Okay, I guess we can get started. So we're at that point in the semester where you should probably do an exam so that you don't have such a ridiculous amount of stuff to study for a single exam. It's already going to be quite a lot of material to go through. So our first exam will be in 2 weeks. No class next week though. So it'll cover everything from the beginning of class through what we finish up today. So next week, no class. If you're doing a hazard assessment, the first part of your hazard assessment is due next week. So it gives you a couple weeks to not only get that done, but also prepare for the test. So the test, as I said, will cover everything from the beginning of the semester through what we go through tonight. It'll focus mostly on concepts. I'm not going to ask you like scattered little facts and figures, but I certainly will spend a fair bit of time talking about different ways to generate magma. We talked about 3 main ways: decompression, changing the pressure, adding heat by adding new magma, and changing the melting point by adding water into the rocks that are to be mantled and changing their melting point. We spent a fair bit of time talking about fluid properties of magma, Newtonian fluids, Bingham plastics, what that means. And then we finished off last week talking about the conditions necessary to cause an eruption. I'm going to go back through that today at the beginning of class, and then we're going to get into how we classify eruptions. So today we're going to spend a lot of time watching videos of eruptions because it's actually necessary to see the activity in order to understand one of the ways that volcanologists actually classify volcanic eruptions. So that's kind of where we're going with that. So it'll be a series of short answer questions mostly. I don't have any big essays, but I'll probably have a few where you're asked to calculate something about fluid properties of a magma, and then I'll ask you a question about it after. If for some reason you blow the calculation part, that doesn't mean you blow the next part. I'll read your answer in light of what you calculated and grade your second part of the answer based on that. I will probably send you an email next week just reminding you of the exam, reminding you that we don't have class next week. I should have thought a little more about the exam by that point and have a better idea what the questions are like, and I can give you a few tips on what to emphasize, but I guess that's all I have on that for now. Do you guys have any questions? Okay, so last week we finished up talking about ways to trigger a volcanic eruption. And let me go over here. So if you're doing this online, or for those of you in class, if you go back and look at this video for tonight, there's lots of videos within the video, and PowerPoint does not allow me to make a video of a video. So I'm going to have lots of links to the videos that are in tonight's class on the same web page that you will find the video for the lecture tonight too. I'll have all of the links on there so that you can go back through and watch all this stuff again, okay? Just so that you know how this is going. So last week we ended up with conditions for a volcanic eruption. Let me see if I can do this. And in order to get a volcano to erupt, your magma pressure has to exceed the lithostatic pressure plus the strength of the rock. And in order to get a system in equilibrium, out of equilibrium, and get it to erupt, there's really 3 ways of looking at this equation to do that. One is you can increase the magmastatic pressure. That's usually done by increasing the buoyancy, making the magma more buoyant. We'll talk about review talking about how to do that. Or you can lower the lithostatic pressure. And remember, the lithostatic pressure equals the depth times the density times the gravity. We're not going to change the gravity here on Earth. For the most part, we're not going to change the density. This is density of the overlying rock, so it's whatever's sitting over your magma chamber. There's no easy way to do that. The easiest way to lower the lithostatic pressure is to decrease the depth of the rock that lies underneath, that lies over the top of the magma chamber. So you can do that by unloading, having a landslide remove material from a volcano. You can have, and that would be a quick way to do it. But you can also have longer term processes that lower the overburden. One would be plates that move apart, extensional tectonics, either at mid-ocean ridges or even in places on the continent like what we have in the Basin Range in the United States, where it's under extension, the crust is thinning over time, and that lowers the depth of the material over your magma chamber. So we talked about some of those ways. The final way is to reduce the rock strength. You could keep the magma pressure the same, you could keep the lithostatic pressure the same, but if your rock slowly loses its strength over time, then if you have a magma chamber with excess pressure, it may be able to break through the overlying rock just because it becomes weaker over time. And typically that occurs as the magma loses gases and volatiles. Most of them are acidic. So what they're able to do is interact with the overlying rock, which a lot of times is silicate based. And when you put hot acids in contact with silicic rocks, you go through a process of hydrolysis, which turns those hard rocks into clay, greatly lowering the strength of the material. In a place like Mount Rainier today, if you've ever been to Mount Rainier, you know that it has an extensive hydrothermal system. You can actually go there and see areas where there's lots of fumaroles coming out of the ground. If you go hike up it, you'll see lots of areas that have just turned to mud and clay. It's basically rotting from the inside out. And what the big concern is there for people who are in charge of predicting eruptions is that that volcano is going to erupt without any warning at all. It's just going to happen as perhaps the rock gets really weak through this continual hydrothermal rotting. That pressurized magma that clearly already exists in there is just going to erupt without much warning at all. Or be weak and have a big landslide, and then you have both sort of things going on, where you're getting unloading from the removal of the hydrothermal system that's all weak rock, and the weak rock itself. Yeah, you had a question? Yeah, I mean, and that's kind of what's going on up there. If you live in the Seattle, Tacoma area, the people who live there, I have a daughter who lives up there, they know that an eruption or a landslide really could happen at any time. They're hoping there's going to be some sort of precursory activity like they had at St. Helens, where there were small explosions that lead up to it, but there have been more than a few instances where volcanoes have erupted with no warning at all. And typically, that ends up being blamed on a decrease in rock strength over time. Okay, so what I have is, I actually put together a little video of this. I think it's worth watching just because it's more visual. I put this together for TED Talks over this last year, and they had an animator and all sorts of things. It's at a lower level than what you guys are learning, but hopefully it'll be worth watching. So I'm just going to let this run. I can make it work. Oh.
heard thunder coming from his cornfield.
I'll start that over.
However, the sound... In February of 1942, Mexican farmer Dionisio Pulido thought he heard thunder coming from his cornfield. However, the sound wasn't coming from the sky. The source was a large smoking crack emitting gas and ejecting rocks. This fissure would come to be known as the volcano Paracutin, and over the next 9 years, its lava and ash would cover over 200 square kilometers. But where did this new volcano come from, and what triggered its unpredictable eruption? The story of any volcano begins with magma. Often this molten rock forms in areas where ocean water is able to slip into the Earth's mantle and lower the layer's melting point. The resulting magma typically remains under the Earth's surface thanks to the delicate balance of 3 geological factors. The first is lithostatic pressure. This is the weight of the Earth's crust pushing down on the magma below. Magma pushes back with the second factor, magmastatic pressure. The battle between these forces strains the third factor, the rock strength of the Earth's crust. Usually, the rock is strong enough and heavy enough to keep the magma in place. But when this equilibrium is thrown off, the consequences can be explosive. One of the most common causes of an eruption is an increase in magmastatic pressure. Magma contains various elements and compounds, many of which are dissolved in the molten rock. At high enough concentrations, compounds like water or sulfur no longer dissolve, and instead form high-pressure gas bubbles. When these bubbles reach the surface, they can burst with the force of a gunshot. And when millions of bubbles explode simultaneously, the energy can send plumes of ash into the stratosphere. But before they pop, they act like bubbles of CO2 in a shaken soda. Their presence lowers the magma's density and increases the buoyant force pushing upward through the crust. Many geologists believe this process was behind the Paracutin eruption in Mexico. There are 2 known natural causes for these buoyant bubbles. Sometimes, new magma from deeper underground brings additional gassy compounds into the mix. But bubbles can also form when magma begins to cool. In its molten state, magma is a mixture of dissolved gases and melted minerals. As the molten rock hardens, some of those minerals solidify into crystals. This process doesn't incorporate many of the dissolved gases, resulting in a higher concentration of the compounds that form explosive bubbles. Not all eruptions are due to rising magmastatic pressure. Sometimes the weight of the rock above can become dangerously low. Landslides can remove massive quantities of rock from atop a magma chamber, dropping the lithostatic pressure and instantly triggering an eruption. This process is known as unloading, and it's been responsible for numerous eruptions, including the sudden explosion of Mount St. Helens in 1980. But unloading can also happen over longer periods of time due to erosion or melting glaciers. In fact, many geologists are worried that glacial melt caused by climate change could increase volcanic activity. Finally, eruptions can occur when a rock layer is no longer strong enough to hold back the magma below. Acidic gases and heat escaping from magma can corrode rock through a process called hydrothermal alteration, gradually turning hard stone into soft clay. The rock layer could also be weakened by tectonic activity. Earthquakes can create fissures, allowing magma to escape to the surface, and the Earth's crust can be stretched thin as continental plates shift away from each other. Unfortunately, knowing what causes eruptions doesn't make them easy to predict. While scientists can roughly determine the strength and weight of the Earth's crust, the depth and heat of magma chambers makes measuring changes in magmastatic pressure very difficult. But volcanologists are constantly exploring new technology to conquer this rocky terrain. Advances in thermal imaging have allowed scientists to detect subterranean hotspots. Spectrometers can analyze gases escaping magma, and lasers can precisely track the impact of rising magma on a volcano's shape. Hopefully, these tools will help us better understand these volatile vents and their explosive eruptions. Did you?
Okay, so that's just a little visual. I want to spend just a couple minutes talking about one thing that we went through last week in relation to that, and that's how cooling magma can increase this magma static pressure here. Because it seems, I think, counterintuitive to a lot of people. It's like, well, if the volcano's cooling off, why does that make it more dangerous? It has less energy, it has less heat, but in fact it does, and it works something like this. So let's say that right here is your volcanic slope here, and down here is your magma chamber, some depth, usually several kilometers. So let's just look at a little parcel of magma that's down in that magma chamber. And let's say, just to make the math work out here, that the concentration of volatiles in that magma is 4.9%. Okay? That's the concentration. So 4.9% of that magma is volatiles. Water mostly, CO2, sulfur gas. Now here, I'm telling you that the solubility of these gases in the magma is 5%. So in the magma here, where are the volatiles? If their concentration is 4.9 but solubility is 5%, where would you find the volatiles? Where do they exist in the magma?
They're dissolved in it?
They're dissolved in the magma. You know, it's like, I use the analogy 7-Up a lot of times. If you look at 7-Up in the clear bottle, you usually can't see many bubbles, right? That's because those volatiles are actually dissolved in the liquid. And that's exactly what's going on with this. It's dissolved in the liquid. Now, if you increase the concentration to 5%, and then increase it a little more, what happens to those bubbles when the concentration equals the solubility? That's when they come out of solution and start forming bubbles, right? But in this situation, we don't have any bubbles, right? And what we want to do is we want to increase the magma static pressure by increasing the buoyancy. And as we have this situation here, that doesn't exist. There aren't going to be any bubbles in the magma. There's not a high enough concentration to allow bubbles to form. So the magma static pressure just sits there, okay? It just pushes back on the overlying rock that you have above it, okay? But, you know, this magma is only a few kilometers from the surface. That's relatively cool rock compared to where it formed, deeper in the mantle. So it starts to cool off. And one thing we know is as you cool off the magma, bring it below the melting point of some of the minerals in there, that minerals are going to form. And if you follow Bowen's reaction series, the first minerals to form, you have olivine, calcium-rich plagioclase, then you have pyroxene and still pretty calcium-rich plagioclase. None of those minerals incorporate any water into them at all. The water stays behind in the melt. So let's say you add a few percent solid crystals in here. And those crystals don't incorporate any water at all. There's no water, there's no other volatiles in them at all. But the only mineral in Bowen's reaction series, at least the top part of Bowen's reaction series, that incorporates any water at all is amphibole. Amphibole can incorporate a little bit of water. As you get farther down, muscovite and biotite can incorporate a little water. But at the high end of Bowen's, none of those things incorporate any water at all. So that water remains in the melt, right? But now you have less melt. You have the same number of volatiles, but you have less melt. What does that do to the concentration?
It
it increases the concentration. It doesn't increase the volatiles, it just increases the concentration within the melt. And if you exceed then that solubility by reducing the melt, then you're going to create some bubbles. And actually, you might create quite a few bubbles. Once you create those bubbles, then suddenly you have a buoyant force, and you've increased the magma static pressure. So you increase the pressure by cooling it off. So yeah, sometimes the volcanoes that just sit there a long time, they're actually increasing their pressure to a point where maybe they can erupt. This was definitely the way that all of the dome building eruptions at Mount St. Helens that occurred after 1980, definitely driven by this process. Lots of studies looked into the growth of bubbles and the growth of crystals and the timing of the eruptions. And it's pretty certain that this is what drove that 5 to 6 years of dome growth. Just the magma chamber sitting there cooling, crystals growing, bubbles growing, and little batches of magma being driven up to the surface. All right, any questions on that?
Yeah.
Yeah.
So you track that with lasers, the mountain growth?
As in the video before? Yeah, that's one of the ways, one of the primary ways and tools that we have to monitor an active volcano. All that shows is that something is moving into the actual cone itself and pushing out on the flanks. It could be driven by this process, but it could be driven by one of the other processes too. Anytime you get magma moving in the volcano, it changes its shape enough that we can detect with LiDAR or really good surveying equipment. So not just this one, but all of those triggering mechanisms we talked about last time. Extension, unloading, new volatiles being brought in, or in this case, crystallization of anhydrous minerals.
So specifically this form of influence on eruption, how would you track that?
So how is this proven exactly for places like St. Helens? You can actually look at so when this material erupts, let's say that this material right here now erupts, okay? Comes up to the surface. And if you look at it, it's got maybe 20% bubbles and maybe 30% crystals. That means that 50% of it is still this melted stuff over here. And you can look at the isotopes of the volatiles that remain to see how much of the gas is actually bled off. So it's mostly through isotopic studies, which I don't know if we'll get into in here, but it would take me probably a good hour to go through how isotopes work with volatiles to give you the background to understand that. I can just tell you that it's mostly from hydrogen isotope studies of volatiles that remain in the lava. So I know that's not a very satisfying answer, but to really answer your question, it would take a whole class period. I can put you onto it, though. I'd be happy to do that. Any other questions I can't answer? Okay, let's move on. Okay, so up to this point this semester, we have looked at how to generate magma, and now how to get volcanoes to erupt. And now once they're erupting, we need a language to talk about them. Usually one of the first things we do in geology when we're talking about minerals or rocks, or in this case volcanoes, we classify them. Rather than talk about 4,000 different minerals, we classify minerals into silicates and oxides and sulfides and things like that. Do the same thing with fossils. You have reptiles, you have mammals, you have all the various groups. We're going to do that with volcanoes too, so that we don't have to talk about every eruption separately. So we'll look at eruption styles and types and various ways that volcanologists have tried to classify these through the years. We'll look at the pros and cons of each method and look at some eruptions. So how do we classify eruptions for volcanoes? Well, there's actually several different schemes that have developed through time, and we'll just do a quick rundown of each of these. We can classify volcanoes by where they erupt. And basically there's 4 different environments that we talk about in terms of where volcanoes erupt. Submarine, below water surface, here on Earth. Mostly below ocean surfaces, but volcanoes have erupted into lakes, large lakes. We can consider those submarine eruptions too, because the pressure is different and the cooling conditions are different. Subaerial are volcanoes erupting on land. Subglacial, volcanoes erupting through ice caps. And finally, planetary eruptions that occur on other bodies in the solar system. Submarine eruptions are still a great mystery. We have very little data. There's only a handful of people that actually study these things.
Is this classified differently from like the mid-ocean ridges? So these are like
These,
think of volcanoes on land.
most submarine are mid-ocean ridge volcanoes still under the surface. There's actually a type of eruption we're going to get to in a minute where it transitions from submarine to subaerial. Actually, enough material builds up that it pops out as a volcanic island.
Okay.
But most of these will be along tectonic boundaries in the ocean.
Okay.
Most of the time, they do it unnoticed because these eruptions usually don't have much seismic activity associated with them. The path is, you get seismic activity when rocks break or when large volumes of magma move up towards the surface. Both of those things give off lots of good seismic signals. Once the eruption starts, the rocks are already broken. It's already sort of carved a path to the surface. So you don't get much additional rock breaking, so you don't get many earthquakes. And these are usually fairly small volume, far away from seismometers. So any seismic signals given off by the rising magma just never make it to seismometers that are on land. So a lot of times we don't even know these are happening. Now, if you're a sailor out on the ocean, sometimes you run into evidence of these eruptions because some of them can actually be explosive. You can have underwater explosive eruptions that produce pumice, just like you do on some of these large subaerial volcanoes. And what you end up with are extensive pumice rafts. This is actually a really tiny one in this image, but there are pumice rafts that can be tens of miles and tens of square miles in area. And, you know, folks out on ships in the ocean just run into these things every once in a while. So that's about the only evidence sometimes that we have. And then sometimes we have submarine eruptions that are occurring pretty close to the ocean surface, and they will actually erupt through the ocean surface. This has happened in the Mediterranean several times. It's happened off the coast of Iceland numerous times. It's happened around Japan many times. So these are areas where you have usually rifts, but sometimes underwater hotspot volcanoes that are building constructs on the seafloor that are getting tall enough to be very close to the surface, so the eruptions actually go through them and you can see them from the ocean surface itself. Probably the one that takes the most attention here in the US is a small, soon-to-be island off the east coast of the big island of Hawaii. There's an island growing out there. It's within a few thousand feet of the ocean surface. It has frequent eruptions, although not very well studied. And just given the growth rates of the other Hawaiian Islands, it's likely that this will poke its head out and become subaerial within a couple 100,000 years. Depends on sea level. Depends on whether the rate of volcanic growth changes or not, but in a couple 100,000 years we should have another Hawaiian island. And then the big island will shut off and most of the activity will focus on this new one, which is already named Loihi. Subglacial eruptions are kind of neat because they follow a pretty well-defined pattern of eruption. And that well-defined pattern of eruption leaves behind a really well-defined stratigraphy. If you go to Iceland, there's lots of features called tuyas. These are sort of flat-topped mountains or domes that have a really distinctive, sort of odd stratigraphy. And they're indicative of material erupting at first beneath a glacier into the water that it's melting from the heat, and then eventually as it melts away and blasts away all of the water and ice above it, it becomes a subaerial eruption. So it sort of transitions from a wet environment to a dry environment. So what you have at the base of these tuyas are pillow lavas. And these pillow lavas, you probably saw them in physical geology, maybe talked about them in historical. Has anybody not seen pillow basalts or talked about them in any of their classes? Yeah, they're mostly just sort of pillow-sized blobs of basaltic magma. That's what they look like. They look like a bunch of pillows stacked up on top of one another. And they're indicative of subaqueous eruptions. Typically in seawater, but as I said before, they can also occur in lakes, or in this case, in meltwater from a glacier. So you get pillow lavas at the base as they erupt into the water that's created by melting the ice above. And then you get lots of ashy, clayey breccias that are indicative of what we call phreatomagmatic eruptions. So there's new magma coming in this case basaltic magma, and it's interacting with the meltwater in a explosive manner. So you get lots of ash, but since you have a lot of water, and since that water's hot, and there's lots of steam, it accelerates this process that we talked about the last 2 weeks called hydrolysis, which turns hard silicic rock into clay. It's the same process that we just discussed when we talked about hydrothermal alteration. We have gases coming out, heat, and when you have acids and water and heat, you have a very vigorous system for producing hydrothermal alteration. So a lot of those ash particles actually turn to clay pretty quick, and that's where that term hyaloclastite comes from. It's kind of a clay-rich, ash-rich, broken breccia that typically forms in these shallow water explosive eruptions. So that sits on top of the pillow lavas. And then typically at the top you have regular old, everyday basaltic lava flows, A'a flows or Pohoihoi flows, depending on the speed of the eruption. So basically you start out with this underwater eruption caused by the melting of the ice, followed by explosive phreatomagmatic eruptions as the amount of water starts to wane and you get more explosions through the shallow water body that's being heated and flashed to steam by all this material coming in. And then once everything's melted and all the water's blasted away, then it just erupts like the salt would erupt anywhere else, either or Pahoehoe, or sometimes just really blocky. So yeah, if you look at this picture in the background, maybe the bottom quarter or so is going to be pillows. Then you'll have a zone in the middle that's all this broken, clay, nasty hyaloclastite, and then lava flows capping the top. And there's lots of examples of this if you go to Iceland. Here's kind of a little diagram showing first pillows forming here in the water of the melting ice up above. Once you get really shallow, you start to get more explosive eruptions. And then later, the lava flows predominate, and you get this sort of three-tiered stratigraphy of pillows, hyaloclastites, and then lava flows. Okay, any questions on that? I think I have some video of Iceland erupting. So this would be sort of what the second stages look like. You don't really see the first stage because it's still beneath the ice. And lava flows, we can watch lava flows a little later, but this is sort of this middle phase that not a lot of people actually get to see. So this is from a few years ago in Iceland, 2 minutes long or so. So I'm just going to let it play and you can watch. Typically when you see that black ash like you do there, mixture of white ash and black ash, the black is wet.
The pilot is confident that a strong northerly wind is carrying this ash and steam away from the helicopter. I'll take his word for it. Oh, look at the lightning. So much energy in that. You see forks and folds of lightning quite frequently now. There's another one. All about the you can also see big pot burns in the ice. That's pieces of molten lava going into the snows. Now look at the stuff coming off the left hand of the flume. Look at the debris there. Large pieces of rock and lightning. So much kinetic energy being released. This is not a nice little bonfire like we had earlier. This is catastrophic. Whoa, look at the lightning stuff there. Stay here. Can you stay? I can't. The wind is just too strong. Okay.
Okay, so that was just a quick clip. We don't have to look at Corey. Let's get rid of Corey. Okay, so again, that's a phreatomagmatic phase of that tuya formation. So lots of interaction between the really hot magmatic material coming up and the colder meltwater above. Okay, so that was our first way of classifying eruptions. We can simply talk about where, and that's useful, but especially if you look at the subaerial that we have the most visual data for, there's lots of variety in the subaerial eruptions, from lava flow eruptions like you get in Hawaii to big explosive caldera forming eruptions like you get in Yellowstone and everything in between. So this is probably not detailed enough for a lot of the work we do. So we're going to look at some other schemes that we have to classify some of these eruptions. Some eruptions are classified by where the vent is on the volcano. I think the first week I had you guys all draw a volcano. This is the one you probably drew. You probably drew Kluichevskoy, which is in Kamchatka. It's one of the best volcanoes in the world. It's 15,000 feet high, and comes right up off of sea level. So 15,000 feet of relief.
That's gotta be impressive.
It's ridiculous, and it's always erupting. It's got eruptions going on constantly. You might get a break for a few months, but it's erupting today. And it erupts out of this top summit vent and does it in a nice symmetrical pattern. It is a beautiful volcano. But not all volcanoes only erupt out of their summit vent. There are other vent locations. You can have a flank vent. Hawaii is famous for this. One of the biggest eruptions of last century was the Katmai eruption up in Alaska. It's now a national park. And no one really witnessed the eruption. There's nobody up there watching it. And even so, it was so powerful and explosive, you couldn't really see much. All you saw was just this tremendous column of ash coming out of the area. And when geologists went up later, they found just the weirdest thing. They found a caldera where the summit had collapsed, but they couldn't find any evidence that material actually came out of it. And it was the weirdest thing. It took them a long time, but a couple miles away, they found a volcanic dome that had formed called Nova Rupta. It was only a few hundred meters across, and all of the explosive deposits were super thick right around this dome. Thousands of meters of pyroclastic material. And it seems as though that this side vent had drained all of the magma out of the chamber, and the chamber was beneath the summit, and once the material was drained out, the whole thing collapsed just like other calderas do. But usually it happens that the collapse occurs in the vent that the material is coming out of. This one didn't. It occurred out of a flank vent. So it was really different, really interesting, and took geologists a while to sort of piece that together. But they did that just by looking at the thickness of the deposits. The thickness of the deposits up around here, super thin. Thickness of the deposits down here, ridiculously thick. And then, I showed you this last week, but here's Hawaii. And same thing sort of happens here, where you have a caldera up on top, and you get eruptions up on top. But you can see over the last, this material down here, all this dark stuff, all this erupted since 1983 to 2018, so a 35-year period, sort of erupted just about all of this. Some of this came out in the 60s over here, but you can see most of the eruptive activity wasn't really up at the summit. And here you have another caldera at the summit as well. So when material drains from here down the rift, or here you can see some older on the southwest rift, then the material up here can collapse. So these are flank eruptions, where the focus of the activity is on the flanks. And in Hawaii, we probably get a lot of submarine eruptions on the flank as well. Most of the flank is under the sea surface. Remember, only a few thousand feet of the volcano actually sticks out above the ocean surface. 17,000 feet of it is beneath the surface. There's a lot of eruptions that happen just offshore. So that's the second way we can classify eruptions, is by the type of vent, whether it's a summit vent or a flank vent, or a rift zone, or whatever the feature is that the material exits through. A third way we can classify eruptions is by the major activity, the primary activity that occurs. And in this case, it's effusive versus explosive. Effusive meaning flowing, lava flows, or explosive, where we have fragmented material that is blasted out of the volcano. And on the bottom here, we have kind of a useful way of thinking about this in terms of kind of the two primary properties that we think about when we try to determine how a volcanoes behave. We look at magma viscosity, from low viscosity on the left to high viscosity on the right. So really runny on the left, thick and pasty on the right. And then on the x-axis here, we have the gas content going from really low to really high. So if you don't want your volcano to explode, what's your gas content? Low, okay? And if you don't want your volcano to explode, what viscosity should you tend towards? Low or high? Low. You want it runny so the gases can escape and not build up pressure. So you want to be down in this area for effusive, right? If you want explosive, you want high gas and sticky magma, right? So you want to be up here. So what this diagram is trying to show is that you basically have a couple of different fields. You have the lava flow field here, and you have the explosive field up above, with kind of a transition zone here in the middle. And all this diagram on the right is showing is that you can actually get lava flows to explode by adding in some external water. What that effectively does is increases your gas content. In this case, the gas is coming from an external source rather than from within the magma itself. So just a couple of ways of thinking about the relationship between gas content, viscosity, and whether or not you have any external water. So low viscosity, low gas, lava flows. High viscosity, high gas, explosions. Pretty simple. If we look at the explosive part, a couple of terms come out that volcanologists use a lot: magmatic and phreatomagmatic. Magmatic eruptions, and you hear this term dry eruption, which I really hate that term. Don't use it. But you'll see it sometimes. It simply means that there's no external water. The only water that you get driving the eruptions is from gases that were dissolved in the magma originally and are coming out of solution into bubbles. Phreatomagmatic, phreato or phreatic means driven by external water. It can be glacial melt, it can be groundwater, it can be lakes, it can be ocean. Just some sort of non-juvenile or non-magmatic and these phreatomagmatic eruptions can be pretty impressive and pretty powerful. They generally occur as distinct blasts rather than sustained eruptions that we'll see when we talk about Plinian, as we will in a some explosive eruptions that are driven by magmatic gases are just powerful and sustained and can go on for days, weeks, and months. Phreatomagmatic tended to be pulsating. Water rushes in, get a big explosion. Water rushes in, you get a big explosion. You just get this pulsating, big blasts. And if you want to see what that looks like, I have one for you here. This is Sakurajima volcano in Japan. It's a pretty cool volcano. It explodes all the time. It's right near a really large city called Kagoshima. If you ever go there, kids walk to school every day with hard hats because the blasts throw stuff all over town, and they have, volcano drills all the time. But this is just some shots of the summit and some of these phreatomagmatic blasts. Probably as groundwater seeps into the magmatic system, you form an explosion, blows everything out, the whole thing sort of recharges, water starts running in. When you get enough water to create an explosion, it does it again. So it's kind of cool because you can see the shock wave coming out of this as well. And you see you can throw some pretty large material out. Those are big blocks. Size of this room. And it takes a few seconds for the sound to travel. So on the scale of things, these are pretty tiny explosions for a volcano. These are not very big. You wouldn't want to be standing on that crater rim. You'd be dead. But compared to some of the other things we'll see, these are small. And then the whole system sort of recharges. That gives you a little better scale there.
It was more than just...
Okay, let's get rid of Corey again. All right, let's take a little break and come back in 5 minutes or so, and we will finish this up.